Hey guys, so in the very first episode of Technical Tuesdays, we're going to be diving into the resistor, which is basically the most widely used lump component out there. We're going to first begin going over some of the basic concepts of a resistor, then dive into the more complex, non-ideal behaviors of the resistor. So we're going to begin with what exactly is a resistor. A resistor is a passive lump component that has two terminals. It's mainly used in circuits to limit current flow. And it's passive because it doesn't require any energy to perform its intended task. Resistors come in various packages. Axial lead, which is mainly used for through-hole and PCB boards. Surface mount, which is just soldered to the surface of the PCB. And in the 70s and early 80s, when surface mount technology was still really expensive, resistors used to be carbon printed onto the circuit boards. So we're going to move on to the three most common types of coaxial lead resistors. We're first going to begin talking about the carbon resistor. It's the tan resistors. You've basically seen them everywhere. They typically come in 1/8 watt and 1/4 watt packages. So if you were to cut them in half, you basically see the outer layer, which is the insulation tube, 2 copper plates that's filled with a bunch of carbon in between. Then we'll move to the thick and thin metal film resistors. Cut that in half, you'd see an insulation tube with the metal film. These vary just a little bit away from the carbon resistors because these typically are a little bit more precise on the values and they manage heat a little bit better. And the most uncommon out of the three are the Wirewound Resistors, which is just basically resistive wire wrapped around porcelain tubes. You mainly see these in power applications because they handle the most power out of the three. When you look at a coaxial lead resistor, you see that it has colored bands around them. These bands depict the value of the resistor. So basically, it goes black, brown, Roy G Biv, without indigo, gray, white. So it goes black, brown, red, orange, yellow, green, blue, violet, gray, and white. And these all correspond to value 0 through 9. And there's also the last band on a resistor depicts its tolerance. Gold for 5%, silver for 10%, and if there's no band on there, 20% tolerance. So looking at a 4-band resistor, it goes band 1 times band 2 times 10 to the power of band 3 plus or minus band 4. You always read a resistor from left to right. And for a 5-band resistor, it's B1 times B2 times B3. And if you ever see a 6-band resistor, it's the same thing as a 5-band resistor with the thermal coefficient for the last band. So, just a quick example, if you have a resistor, you don't know the value, and you read the colors red, 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 gold, it's 2 times 2 times 10 to the power of 2 plus or minus 5%. Which equates to 220 ohms, plus or minus 5% tolerance. Alright, so we're going to move on to equivalent resistances, where when you have multiple resistors connected together and you want to find the equivalent resistance of all of them. So we're first going to begin talking about series, or when the current only has one path to go. So in other words, the current flowing through this resistor equals the current in this resistor and in this resistor. They're all equal. So in series connections, the equivalent resistance is simply just the sum of all the resistances added up. When we move on into parallel, where there's 2 or more paths that the current can flow, the equivalent resistance is 1 over R equivalent equals 1 over R1 plus R1 over R2 plus 1 over R3, or the summation of 1 over all the resistances. So we're going to talk about the ideal properties of the resistor. The first one being the most common formula to electronics hobbyists and electrical engineers, which is Ohm's law, which pretty much says that the voltage equals current times resistor. This is the voltage across a resistor. This is the layman's Ohm's law. It's an ideal property. The real Ohm's law is a little bit more complex, and it's basically a lot more cool to talk about. If you guys would like, we could have a separate video on that one alone because it gets pretty in depth. Then there's also the power dissipated by a resistor, which is power equals current squared times resistance which equals voltage squared divided by resistance. And obviously knowing any of these two, you could solve for the other one with these formulas. So we're going to talk about a few uses of resistors in modern day. For one, we're using resistors as a current limiter, where you either have the resistor in series or in parallel with the load. Both these circuits are fundamentally acting the same. They're both helping limit the current going to the load. There's also a voltage divider, where you have one resistor in series and in parallel with the load. This is not as widely used because as the load changes, the voltage will change. For a voltage divider, this is typically the voltage you'll use. Sometimes used, but you'll rarely see that. Something resistors are really good for is analog to digital converter. This is a resistor ladder R2R, where you have your most significant bit here, and you pretty much make as many bits as you need down using just R2R ladders. Okay, wow, thank God we got the boring stuff out the way. We're finally moving on to some of the cool stuff, the high frequency applications of resistors. We're going to basically find out when a resistor acts as an inductor and when a resistor acts as a capacitor. So basically looking at the view of the carbon resistor. So one thing we could for sure see is basically these two right here look like parallel plate capacitors. So I'm going to be drawing a high frequency model of the resistor. So basically we're going to have one is a parallel plate capacitor. Then obviously we have the resistance right here. So we'll draw it in parallel with the resistance. Then we also get, at high frequencies, we'll get some inductance from the leads. So we could also draw that in here, the inductor from inductance of the lead. So basically from this model is mapping out the resistor at high frequencies. You know, we have a inductance from the lead. We have a capacitance from the parasitic effects. There's obviously leakage capacitance and the capacitance between the two copper plates inside the resistor. So this will be the parasitic capacitance. Then we'll also get just the standard resistance from the resistor. So this is what you use to model a resistor at high frequency. You know, basically from this we're going to derive the function of it, and we can map it how the resistor will act as you increase the frequencies. So I could spend half an hour boring you trying to show you how to derive the formula for that, but nobody wants to watch that. So I'm basically gonna write just the impedance of the capacitor. So with this formula, we see what the impedance of the resistor is as you increase as a function of omega, with omega equaling 2 pi times frequency. So from here, we could basically visually see what the resistor is going to do as we increase the frequency. So you guys saw me write down the formula of the impedance of the resistor based around the high frequency model of the resistor. Looking at the high frequency model, we see that it's an LC circuit, so we could also find the frequency at which the resistor will resonate. So we should also note that, because that's going to, for our graph, it's going to signal the breakpoint where the resistor changes from a capacitor to an inductor. So we could also write that omega naught equals 1 over square root of the inductance from the leads and the parasitic capacitance. And that's going to basically signal us where our graph is going to change. So we'll just label this as omega naught, because on this graph we see on the x-axis it's omega and on the y-axis it's impedance. So I guess we can just start off with the initial value of what does this formula equal when omega equals 0. So we plug in 0 here, we get 0 plus R resistance is not dependent on the frequency, minus 1 omega squared, that's 0 right there, 0, so it ends up just equaling R. So at omega equals 0, we'd expect it just to be R, which is how a resistor operates at DC. With omega equals 0, we know it's DC, so we expect it just to be a resistor. But say as we move up the frequency chart, what do we expect to happen? So we get j omega L here. As frequency increases, this is going to go up, and this is going to go up also, but it's going to be negative. So we should expect this to start climbing down, because the parasitic capacitance is overwhelming the inductance of the resistor. And this is going to basically go down till the resonance frequency. And from here, it's going to change courses and start acting more like an inductor. Because the impedance of a capacitor equals 1 over j omega c, and Z inductor equals j omega L. So you can see based on this chart, well, as the frequency increases, this is going to shoot to 0, which we expect it to. So from this we can see that as the frequency increases but is less than the resonance frequency, the capacitance effect of the resistor will be overwhelming the inductor, and it's going to act more as a capacitor. But eventually you'll hit the break point or the resonance frequency, and this will start taking over the impedance of an inductor basically. And as omega increases, this is going to start shooting off to infinity, and this is what we see from this portion of the graph. So I hope you guys liked my little talk on the resistor. It was a high level talk. I could have gone a little bit more in depth, but I didn't want to bore you guys. Next week I'll be doing it on the inductor. If you guys have any good comments on what I could do to make these better, please let me know, because I would love to hear them. Thank you guys.